Okay, let us have. Heavenly Father, thank you in the name of Jesus. I thank you for this day. Thank you for our teacher, King of Glory. As we're going to begin our lessons, be the one to guide us and lead us and help us understand all that we are going to study. We dedicate this lesson into your hands, Lord. In Jesus' name I pray. Amen.
Okay, I want to welcome each and every one to this very first lesson of Senior S.6 Chemistry. Today we are looking at organic chemistry, and the subtopic we are going to be looking at is alkenes. The teacher is Isaac Nyirimbibi, who is our chemistry teacher that is going to be taking us through this session. I request that we keep on responding using the chat, and also if there is any issue, you raise up the hand. I expect this session to be more interactive so that we can keep on learning, and also if there is any inquiry. I know very well that organic 1 has been covered in Senior 5, and this is one way of helping us recap with what we looked at in Senior 5, and also we see whether we have anything that is still disturbing us in organic chemistry before we dive into our new topic. Those who are writing on our screen, I think, let me see how best we can first handle that, so that we can be able to avoid all these people who are writing on the screen. Okay. So that is our overview. We shall be looking at the structure and reactivity of alkenes. That is number 1. We shall also be looking at describing the structure of alkenes, including what is meant by a pi bond. So when we're looking at the reactivity of alkenes, we shall also look at those chemical properties that alkenes undergo. So we shall be looking at chemical properties of alkenes, its structure, and also we'll be able to describe why alkenes are reactive molecules. So those are some of the questions that we shall be able to understand by the end of this lesson. Now, the first question which we're going to be discussing, there are those 3 questions that we have on the screen. Number 1, what do we understand by alkenes? And then, why are they classified as uncirculated? And also, I request one person to describe for us the structure of alkenes. Can I have the first person to help us understand, give us a brief introduction of what alkenes are? Who is ready? Who is ready? Okay, I can see Mercy. Mercy, you can unmute. Okay, Mercy.
Good afternoon, sir.
Good afternoon. Now, you first wait, but
Yes.
you keep your microphone on, and you first clear the screen such that we don't have this dot on the screen. It may keep on disturbing us. Okay. I believe now it is clear.
Yes.
Okay, good. So, Mercy, you're taking us through the first one. Whatever you tell us, I will be noting it down. So that, and I request that this session becomes very interactive. We have some questions we're going to try out in our notebooks. So let us be ready with our books and pens so that we can be able to discuss. I can see some people are already putting the chat. That is very good. Mercy, be very fast.
Okay. So generally, we saw from alkanes that they were saturated because all their carbon atoms had had all the 4 bonds. In other words, the carbon atom was saturated. However, for alkanes here, it becomes a difference from the alkanes, whereby their structure generally is composed of the double bond between the carbon and the carbon, and then also they are unsaturated.
And they're also unsaturated. So
Unsaturated.
the keywords you have told us about alkenes. Okay, you pardon for us and we hear. What are the keywords?
They are double bonded. They have double bonds. Hydrocarbons with double bonds between their carbon atoms.
Okay, so there is another word you're telling us that they are hydrocarbons with double bond. Okay.
And then unsaturated.
And they are uncirculated. Thank you very much. Thank you. Let me have another person also give us another one description of what alkenes are. Yes, you see, ITEL. Oh, ITEL, are you able to? Any other person? Any other person ready to tell us? Okay, ITEL.
Good afternoon, sir.
Good afternoon. How are you?
I'm okay. Alkenes form unsaturated hydrocarbons. This is because they contain at least a double bond between 2 carbon atoms.
Because they contain a double bond between their 2 carbon atoms. Now you remain on the call. You tell us why are they more reactive?
They are more reactive because their functional group is double bond.
Because
their functional group is
okay, thank you. Thank you. So we have seen that one thing about alkenes, they are hydrocarbons, and we say that the reason why we call them hydrocarbons because they have only a hydrogen and carbon atoms in their structure. And then they are having a double bond, and the double bond, she's telling us that the double bond is their functional group. And we say that these functional groups are the ones which are responsible for the behavior of these compounds. So the functional group they have for the double bond is the one which is responsible for the behavior, how they behave, how they react, is because of the double bond that they have. Okay. Letitia? Letitia? Yes, Letitia. Letitia, are you there? Okay, Dorcas? Dorcas, okay. Dorcas is not unmuting. But I believe we can continue from what we have been able to share. We have been able to see that number one, okay, so we are continuing from where we stopped. That is it. So we are still describing what alkenes are, and we had already discussed that alkenes are unsaturated aliphatic hydrocarbons, and we said that key ones we are seeing here is the hydrocarbon and containing at least one, at least meaning we know very well that we have some alkenes which have more than one carbon-to-carbon double bond. But the key one is the double bond. Every alkene, any alkene that has ever existed, it has a double bond. So that is one of the key ones. And also we said that they have a general formula of CnH2. H2N, meaning we can use this general formula to generate a number of alkenes, as we're going to be discussing as we reach on the nomenclature and looking at the different compounds that we have under alkenes. Now, there's one thing I want us to discuss about the shape of an alkene. So we are seeing that we have the general formula CnH2n. And one thing we have seen that they have a functional group. The functional group we have here, the functional group is the carbon-to-carbon double bond. And we are saying that this functional group is the one which is responsible. To the behavior of all these alkenes. Now, what do we see about the shape or the structure of an alkene? So this is a 3D structure of an alkene, and majorly here we have selected ethene. This is the structure of ethene, and we can see the double bond right here. We have a double bond. They have a bond here, which is the first bond, and then we have another bond here, which is making this the double bond. So this is our functional group that we are seeing. Then these are the hydrogen atoms. We have these hydrogen atoms, and then these black, these ones which are black, these ones are the ones which are the carbon atom. We know very well that the simplest alkene is ethene with CH2 double bond CH2. So this is a 3D dimension. So what is special about the shape of any alkene? There are key points I've noted on the side here, where we're saying that the double bonds are planar. The double bonds of alkenes are planar. What are we meaning that they are planar? They are flat. That is the first thing. That the double bonds of alkenes are flat, or they are planar. And we can see from our 3D-dimension structure here, the one we have drawn here, it can clearly show that the bond angle. Now, the bond angles we're meaning, we're having bond angle here. It is 120 degrees. Even here, approximately to 120 degrees. And even here, we have 120 degrees. So the same case with this side. So the bond angle is 120 degrees. But we can always see this when we draw a 3D structure like this one. If we have something like this here, we may not be able to see a 2D. We may not be able to see the angle. But when we have this, we can easily see the angle that is actually 120 degrees. Now, there's another characteristic that we see in the shape, that they are fixed, or they have a restricted rotation. They have a restricted rotation. And here is the question. Why are alkenes having a restricted rotation? What causes that restriction? Can I have someone to tell us that? We want to answer that question. Where is that restriction coming from? Why is there restriction in the rotation compared to the corresponding alkenes. Anyone who is ready to respond to that? Let me have someone. Okay, good. Imla, you can unmute. Imla? Imla, you unmute, yes.
Yes. Good afternoon, sir.
Good afternoon.
May I think these alkenes have a restricted rotation due to their bonds, like the bonds they do have. For example, for them, they have a pi bond and a sigma bond.
Okay, they have a pi bond and a sigma bond. Do you know how the pi bond and sigma bond come about? You remain on the call. Do you think you can take like from this structure of ours here, this 3 dimension? How can we be able to identify those different bonds, and how can we come up with those bonds?
Now, for example, the sigma bond, it comes, we get these bonds from hybridization.
Very good. I like that. You're using. And?
They all alkenes have the sigma bond, and it lies in all the 3 types of hybridization. However, in each type of hybridization, there is another bond that continues to add on itself. For example, the alkene might but it has the sigma bond and the pi bond. The sigma bond, it's a single covalent bond. It is formed by overlapping the s and p orbitals. If we draw those orbitals, those boxes, they show how arrows are distributed against each other. And the sp2 hybridization, sorry, the pi bond, the other bond, it's also a covalent bond. Rather, it's formed by lateral overlapping of 2 parallel p orbitals of these 2 adjacent atoms. That's what I think.
Oh, thank you. That is good. So the type of hybridization alkenes undergo is called what?
sp2 hybridization.
sp2 hybridization. That is very good. I can see a hand up. Yes, please, you unmute. Edith, you unmute. You tell us your take on that. Yes, Edith. Edith Mbuga. Edith Mbuga, you unmute. You unmute.
Yes, good afternoon.
Yeah, good afternoon.
So when they're asking why alkenes have a restricted rotation, think about it like this. If I have 2 fingers, like I have my left and right hand.
Yes.
And I connect them. And I take those to be the bonds.
Yes.
Now I want my hands to rotate.
Okay.
It's not going to be possible unless I break the bonds. Meaning that this restricted rotation breaks the bonds.
Okay, so which means the restricted rotation is due to the other double bond which is being added, the second bond, yeah?
Yeah.
And now it is going to become even more hard when you go to alkynes. Are you seeing that?
Yeah.
Because now in alkynes, we are going to add another third bond. So they become now 3. Yeah, thank you. That is good. So we can see when we look at this, we can see all this is coming from what we studied about the hybridization. And we see that this one is, and the alkenes undergo the sp2 hybridization. Someone is saying that, please, let's discuss more about hybridization. Okay. He's requesting for more about hybridization, and we are going to have that. Anyone who can tell us what hybridization is by show of hand, so that we can use like 2 minutes and talk about hybridization. Someone is asking, which topic is this? Let me hope you have already studied this topic under organic chemistry, alkenes. This is the topic in senior 5, and now we're in senior 6. So I believe we have already studied that, as someone was asking the topic. Let me hope you have senior 5s here. If you have others who are not in senior 5, they may get now lost. Okay, Chiwana Edward. Chiwana Edward, unmute. Edward, yes.
Yes, good afternoon, sir.
Good afternoon.
Master, I was answering of hybridization.
Yes, please.
Hybridization refers to the mixing up of atomic orbitals.
Refers to the mixing up of atomic orbitals.
Atomic orbital. Yes.
Okay. Now, for example, in this case, we are having sp2. How can you help someone who wants to understand how this one comes about, the sp2 hybridization in alkenes?
Actually,
yes. Okay, are you there? Okay, someone else who can try. I'm seeing Infinix Smart 6. You can unmute. Infinix Smart 6. Infinix. Infinix. Okay, Max.
Yeah, I think it is the mixing of.
Infinix, are you speaking?
Yes.
Yes, please.
Good afternoon.
Good afternoon.
So the S2 and S6 is the mixing up of an electron, like the alkane have 6 electrons. So they have carbon. It has 6 electrons. So it is the 1s2 and the 2s2 and the 2p2. So they get an electron and it sits in the other orbital. One electron sits in the other. That is the mixing up. Something good.
Okay. The mixing up. Can you? Someone is saying that he's not getting very well. Is it true? Hello, can you hear me very well?
Hello? Yes.
Okay. So I wanted you remain on the call. I want to create another space that we can discuss something small about hybridization of alkenes, and then we can wind up with that very fast. Okay, I want to be sure that you are seeing a blank space. Are you able to see the blank space?
Yes.
You're seeing the blank space?
Yes, I'm seeing.
Okay. So I want us to look at the hybridization. Let me write this. hybridization of alkenes. So someone is saying that is the mixing up of orbitals. Who can tell us the configuration, electronic configuration of carbon? Because in this case, we are looking at, when we're looking at this hybridization, we are looking at specifically that carbon atom. So when you look at the carbon atom, what's the electronic configuration of carbon atom?
It is 1s2.
1s2.
2s2.
2s2. Are you seeing what I'm writing?
Yes.
Okay, continue.
And then 2p2.
And then
2p2.
2p2. So what can you say about this electronic configuration? Why is it, are we having here a 1 and here we're having a 2, a 2? Okay. It's okay. But when we see one, when we see a 1 here, and here we're seeing 2, 2, meaning that these 2s and 2p, they're on the same level. Are we seeing that? These ones are on the same level. Are we there? Now, during the hybridization, when you look at the orbitals, the 2s orbital and the 2p orbital, now, the p orbital has 3 sections, and this is a p orbital, 2p orbital. We know that p can get a maximum of 6 electrons, while s can get a maximum of 2 electrons. Let me hope we know that. Are we there?
Yes.
I want to make sure that I'm moving with someone. Then others also can raise the hand. Very good. Imla is saying we are together. So, in this case, the reason why I'm considering 2s and 2p for this carbon atom is because the 2s and 2p are on the same level. Now, there are 2 electrons in here, so we normally put them facing the different directions, one facing up and the other down, to make a pair. Now, in P, there are 2 electrons. We see there are 2 electrons, meaning we are going to distribute them because they have many looms, and therefore you can easily utilize all the looms. So we see that P is remaining with 1 free orbital. Are we seeing that? Now, what happens? There is what you call excitation. So excitation, when excitation takes place, these 2 electrons which are in S, one says, no, there's a free space in the other loom. So it says, let me leave here. And then it goes and occupies this free space in the P orbital here. So which means at the end of it all, we are going to be having, there we are remaining with only 1. And then here we are having all the orbitals having 1, 1, and 1. So here, which means we're having 1, 1, 1, 1. So this is the excited state. But what happens during the hybridization of alkenes? For alkenes, and I'll go what you call sp2 hybridization. You recall we have the 3 types of hybridization, where we have the sp2, we have sp3, and then we have sp hybridization. This one is seen in which ones? Where do we find sp3? In which hydrocarbons do we find sp3? Are you still there?
Yes, I am. I don't know.
Yes? Okay. So in
Could
sp,
they be
it is?
alkenes?
So sp3 is for alkenes. Now, when you see sp3, meaning that because we are going to be using the same excited state of carbon, so here we have the 3p, here we have 1s. All there are 3 electrons in p and 1 electron in s. So when you see sp3, meaning there is 1 s electron which is mixing with 3p electrons to form 4 hybridized orbitals. Are you seeing that? Now, for when you come to sp, meaning that you're going to be having only 1 s electron and 1 p electron, meaning you're going to leave 2 electrons which are not hybridized. So that one is the one which takes place in alkynes. We can even have one another day and we go through hybridization for all these ones, but I'm giving you a glimpse that we can even make more research on the same, that next time we can make more clarifications on hybridization of alkanes. And today we are looking at sp2 hybridization of alkenes. Now, let's see. When you talk about sp2 hybridization, you recall the excited state. We're having 1 electron in 2s, and the other electron which was in s, it came in here in p. And here we have the 3p, here we have only 1. Now, we are saying that in alkenes, it is 1s which is combining with 3p, which is combining with 2p, and then they'll be able to form 3 hybridized orbitals. Because you recall we are looking at sp2. There are 2 electrons in p and 1 electron in s, meaning they are going to form 3 hybridized orbitals, and they are going to leave 1 which is unhybridized. One which is unhybridized. So 1 electron is going to remain unhybridized, and that is the one which causes the occurrence of the other pi bond. We are going to see how this one is happening. Are we moving together? Please make sure that you show those reactions so that we know that we are all moving together. Joan has a question. Let me first respond to Joan before we move forward. Joan, unmute.
Good afternoon, sir.
Good afternoon. How are you?
I'm all right. Teacher, some people say that, okay, what are the rules of writing those electronic configurations?
What are the rules? What are they saying? Okay, what are you saying on that? We can tell us and write here.
Some people say that, for example, when I'm writing 1s2, that the s and 2 must be on the same line with that one. And some people say that even though it's not on the same level.
I'm not getting clearly that when you're writing
the electronic configuration.
Oh, these ones.
Yeah.
Okay. That's what?
Some people say that, for example, that one S2,
yes,
that it must be on the same level with 1. And some people say that even though it's not on the same level. So which one is which?
Okay, I think I'm not getting you clear what you're meaning. Now, this is electronic configuration we're talking about, isn't it?
Yeah.
So we have 1 SC2, 2 SC2, and then you have 2P2. What you're saying that this one should be on the same level with what?
With S and 2.
Same level with S and 2.
Like the way you've written.
Like this.
Yeah.
Then other people say that what?
The same thing, but the way of arrangement. 1 SC2, 2 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 SC2
Okay, the way of arrangement. Can you write it down and okay, you read and I write the one you're talking about.
It's 1s2. Like
1s2. Like that?
yeah.
Okay. So what are you saying, that there's another way, or this is the one you're talking about? Like have you been answered, or there is something that you need more clarification?
Yeah, there is.
There is a question you ask. That's why we are here now. Okay, the question is about electronic configuration. Yeah?
Yeah.
Yeah, because as we discuss, we'll be able to get the areas we can always start with in our next lesson. Like now someone is talking about hybridization for these other, like alkenes. Those are things that we can deal with in our next session. Now, if the electronic configuration is also somehow challenging, we can also deal with that in our next lesson, and we bring even those other questions in the same line. I believe we shall be able to tackle it very well. There is someone who has a hand up, maybe. Yes, Hudson. Hudson, you can first speak and listen. Yes, Hudson. Yes.
Yeah, good afternoon.
Good afternoon. How are you?
I'm fine. Before I add anything else, so you chwado gambi wani mabega. Katukola SP2 hybridization of alkenes wali mazo.
Wano.
Tugabi denti. Ena 3 hybridized orbitals ne one
for one which is unhybridized for alkenes. This one for SP2.
Yes, exactly.
This one, yeah. Here.
Yeah.
Yes.
Then no gamba no yevira ko kuba rotation eringa erichi.
Restricted, and I'm going to show you that I was saying that this unhybridized orbital, which remains unhybridized, is the one which leads to the rise of the pi bond. Are we there? Now you remain on call, and then we see here. Now the clear picture is here. Now the other unhybridized is this one, which is in blue. Are you seeing the blue?
Yeah.
Now this is one orbital, but which is half. So one half goes up and another half goes down. The same case on this other carbon atom. So when you see this carbon atom, it has 4 orbitals, but the 3 have been hybridized. When we say they are hybridized, they have overlapped with another. For example, you look at this. This one has overlapped with the one for this p orbital has overlapped with the one for this other carbon atom to form a sigma bond. Are you seeing that? Then another one, it has combined with the one for hydrogen, the s orbital of hydrogen, and they're also forming another sigma bond. The third one has also combined with another hydrogen atom, to form the S, to form another sigma bond. Now we remain with the one which is not hybridized. On each carbon atom, there is one which is not hybridized. Now for them, they do what you call sideways overlap. So when they do sideways overlap, that's why you're seeing these lines here, this line. So this one gives us a half pi bond. Even this one gives us a half pi bond, thus forming another single bond between carbon to carbon. It's that single bond for pi, plus this one which has been formed, this one, between sp2, sp2, another bond. Are you seeing now they are forming 2 bonds? And the other time, the other person who shall say that when you join 2 hands, it is very hard to rotate your hands when you have joined them together. So this sigma bond which is formed and the pi bond, they are now becoming 2, making it hard to rotate.
Okay, sir.
Yeah, so that is where the restriction is coming from.
Okay, thank you, sir.
Okay, welcome. I want us to continue. So that was our sp2 hybridization. Now let's go to the nomenclature. Now, the nomenclature, I know you know it and we are going to go through it very fast. But of course, we have the task. The task is the one which will help me know that you know it very well. Can I have someone take us through the rules of the IUPAC rules for alkenes? Let me see someone who can take us through. Hansen has spoken something. Let me see another person. Herbert. Okay. Herbert.
Sir, good afternoon, sir.
Good afternoon.
The rules, the first rules is like choose the longest carbon containing bonds. When you look at the second rule is number the chain.
First wait. There's someone who is saying that I pardon on the restriction. Let me use only 1 minute and then you take us through. You remain on the call, okay. Herbert remain on the call. So
it's okay.
When you talk about the restriction of rotation, someone was telling us that let us try it out. Get your two hands and you join one finger on one side and another finger on the other side. Have you all done that? If you have done that, let's try to rotate. Is rotation very okay? When you rotate, when you have joined the one finger from one side and the other side, can you easily rotate? Now, Hami, please, let's try it out. When you get two hands and you join them together, because we are looking at two things, when you have a single bond and when you have a double bond. So when you have a double bond, rotation becomes somehow hard compared to when you have a single bond. And as I said, Gloria, you're talking about hybridization. As I said, now that one is going to be our major focus. As we come back in our next lesson, we look at hybridization in full, as we look at hybridization for alkenes, alkynes, and alkenes, all of them at once. Here, I was giving us a sample, and as I said, we can now go and make research that next time in our lesson. We already have that knowledge, and we are just discussing the hybridization. But we are trying to use hybridization to explain the restriction of the rotation taking place. I believe that one is clear. So next time, in our next lesson, we shall emphasize more on the hybridization. Nomenclature, you can take us through.
Yes, Master. If you look at the first rule, it is choose the longest carbon chain containing the carbon-to-carbon bond.
Okay, good.
Then the second one is number the chain to give the double bond the lowest possible number.
Okay, good.
Then the third one is replace an with the in.
Okay.
An with the in.
Okay.
And let's scroll it down a bit. It's kind of fading. Scroll down a bit, Master.
It is not okay. Are you seeing now?
Yeah, it is clear. So the fourth one is indicate the position of the double bond.
Okay, someone who is asking for the notes, I'm going to share this one in the group. They will be able to share it.
Then the last one is name and number the chain.
The side chains. The side chains.
Yeah.
And they are saying that if what? Present.
If present,
okay.
Yeah.
Now, I want you to name for me this first example. Example. We have this example. Okay, let me use here CH3. We have this example. Please, even other people, let's look at this example and then you put in the comment section there the name of this compound. The name of this compound. Okay. Let me see your answers, please. What's the name of that compound we have there? That is A. I'll also put B. That is B. So let's start with those ones, then after we do our practice. I can see someone saying methyl. I can see different answers. Now let me have one person who is raising up the hand to tell us the answer. How about, were you still there? Let's have Loda Faith. Loda Faith? Faith Loda?
Yes, teacher.
Which one are you taking?
It's the first one. Part A. Part A, it's 2-methyl butene.
2-methyl.
Methyl butene.
Butene. Butene, like this? Like that?
Yeah. Yes,
okay.
Teacher.
Okay, thank you. Let me have another person. Someone saying that, okay, 2-methyl butene, even the one in Airtel. How did you come up with this one? Can you tell us how you have come up with this name? Okay, yeah, it's gone. Okay, the second one. Someone is saying 2-methyl but1-ene. 2-methyl but1-ene. Hudson. Hudson is saying 2-methyl but1-ene. The position of the double bond. I'm seeing people are not showing us the position of the double bond. Pavin is saying 2-methyl but2-ene. Okay, good. So people have started putting the position of the double bond. Now someone is saying 2-ethyl. Okay, that is for part B. Okay, thank you. So there's one thing I'm seeing here. They are saying choose the longest carbon chain containing the carbon-to-carbon bond. Okay, so John has been able to tell us this. So we want to see which one is our longest carbon, which one is our longest chain, and the one which is containing the carbon-to-carbon bond. So when we see the different chains we have. If you start from this side, we have 1, 2, 3, 4. Then we also have this one from here. 1, 2, 3, 4. We also have from this side 1, 2, 3, 4. So which means if we start from any side, we still get 4 carbon atoms. But now, they are saying that number the chain to give the double bond the lowest possible number. Which one gives the lowest possible number? When we start from this side, the double bond gets a 2. When we start from this side, it gets a 2. From here, it gets a 2, which means any side still works for us. Then we press N with in, then indicate the position of the double bond. So the one who has given us this answer forgot the position of the double bond. Because when you see the position of the double bond here is on carbon number 2. So we have to indicate it. So which means since there are 4 carbon atoms, it becomes butene. But the double bond is on 2, so we have but2-ene. And then we also indicate the chain. Because they say that name and number side chains if present. So there is a chain here. And on which position? You have to make sure also give it the lowest possible number. If we start from this side, the chain gets the third. Are you seeing that? If we start from this side, the chain gets the second position, which means it's good for us to start from this side, going the other side. So that our chain is on position number 2, and then becomes 2-methyl butene. The position of double bond 2-ene. Very good. So this is good, but it was lacking the position of the double bond. Okay. I'm seeing someone who has a hand. Yit. Someone who is having the name Yit. You unmute. Yit. Okay. Mark. Cynthia Maria. Cynthia Maria. Unmute. Cynthia Maria, are you ready to tell us for part 2? Okay.
Yes.
Yes, part 2.
Part 2 is 4-ethyl pent 2-ene.
Yes, slowly. 4-ethyl pen. 4-ethyl what? 4-ethyl what? Oh, you have disappeared. Okay. I can have another person now. Audrey. Audrey, where are you? Audrey. Audrey, you unmute. Okay.
Good afternoon, teacher.
Good afternoon.
My response is 4-ethyl pent 2-ene.
Pent 2-ene. Where did you count coming from?
From my left-hand side going
From
to
here?
my right.
From here?
No, the other side.
From this
The
side?
other side, yes.
So you
yes.
said 1, 2, 3, 4, 5.
Yes.
What about when you come from a 1, 2, 3, 4, 5, 8? Are you seeing that this is not the longest chain? Are you seeing there is a problem? Okay, let's try and see. If I start from here, this is 1, yeah? 2. This will be 3. This will be 4. This will be 5. 6. Now this one becomes long. Have you seen it?
Yes, teacher.
We have another longest chain. And and actually, even this one, our branch is not ethyl. Our branch is not ethyl.
Some methyl.
Now, what is the answer?
I'd say 3-methyl.
3-methyl?
Yes, 3-methyl. Hexane. Hex 4-ene.
Hex 4.
Yes, 4-ene.
So this means that the double bond is on carbon 4 and the branch is on carbon 3. So let's prove it out and we'll see. So we have 1, 2, 3, 4. Okay. 1, 2, 3, 4, 5. So is it true? Okay, thank you. Let's have another person and see whether it is true. Let me have someone saying, Ethan Magala is saying that is okay. But is someone saying, Nubian, what are you saying? Joshua, okay, Joshua, you unmute and tell us. Joshua? Okay, Joshua.
Yes, sir.
Tell us. Are you agreeing with her on that response?
No, I'm not agreeing.
Very good. Tell me, what is your response?
For me, I think it is 4-methyl.
Okay.
It is
Let me write it down. 4-methyl.
it is 4-methyl X2 in.
X2 in. So where did you start counting from?
On my left.
On your left. Okay, let me count with you and we see which color will be the best to count here. So you started from here?
Yes.
1, 2, 3, 4, 5, and 6. So on carbon 2, there is a double bond. Yeah?
Yes.
Good. On carbon 1, 2, 3, 4. On carbon 4, there is a methyl.
Yes.
Okay, let's see. Did you follow the rules? So they say that choose the longest carbon chain contain carbon to carbon. That was done. Number the chain to give the double bond. So the double bond is the one which is supposed to be given the lowest possible number. So I believe that one becomes a correct one. That is a correct one. Can we clap hands for him, for Joshua? Let's clap hands for him using those reactions. Let's clap hands for Joshua. That was a very, okay, good. Shamis, I can see. Good. Anyone with a question on nomenclature, because I want to give you your task and we try it in 10 minutes. Okay? There's a question. And if you don't have a question, please, let's put down the hand so that I can know who has a question. Blessed daughter. Blessed daughter. Blessed daughter, do you have a question? Okay. Jovix. Okay, blessed daughter, you're speaking.
Mister.
Yes.
Good afternoon.
Good afternoon, how are you? What were you saying? Hey, you have disappeared. Okay. Hudson, you have a question. Hudson, you have a question before we proceed. Hudson, I'm looking for you. Is your hand up, Hudson? Blessed daughter, you're not speaking. Hudson, you speak. Hudson? Hudson, you speak?
Okay, so I have a question before we proceed.
Okay.
So first of all, my question is on the branch.
Yes.
So if you look at the branch, we say it's methyl, but my question is, see on the branch we have CH2 and CH3.
No. You see the branch we have considered. I mean the long chain. Are we together? Look at this. Look at this. Our long chain is this one. Have you seen it?
Yeah.
Yeah. Have you seen that now the branch is methyl, not ethyl?
Okay. I'd considered another approach.
Yeah. Okay, I think now it is clear. Now, to know that you have understood, try out these numbers. Let everyone start. There are the numbers. Write the correct IUPAC name for those ones. Let me hope you know that every corner has a carbon atom.
Yeah.
Let me hope these ones are not going to confuse us. Let me rewrite this one so that you can get to know what. So here it means there is a carbon atom, which is CH3. Then here there is a carbon atom, but there is a double bond. So here there will be H and double bond, and then we shall be having CH2. So we need the name for that. So this is another way we can write this one. Someone is saying that it's reduce on the screen. You people, you're not seeing? I reduce or I should increase? Hansen, are you seeing the screen very well?
Yes,
Okay.
sir.
Yeah, people are saying that we maintain. Okay. So please, let's start naming. So I want to start, when you're putting in the comment section, put number 1, you put the name. Number 2, you put the name. Number 3, you put the name. Like that. At the right time, I'm giving you 10 minutes. So by 3:20, we should be done with nomenclature of these ones, all these 5. I'm trying to put down these ones to make it clear for some people. Here, allow me to be doing my work as you also do your work. So by now, I don't expect hands up until when we are done. When I tell you now it is time to respond, but we can be, please don't put one by one. First, at least do like 3 of them, and then you put the answers for number 1, number 2, number 3 at once. That we can do a number of things at the same time. This is it. Okay. Someone is saying that he's new to this. So some people have not covered organic chemistry. But even if you have not covered, don't worry. That's why we are here, to make sure that we get to know. We get to know how to do all this. Yeah, I can see some people have finished the 3 numbers. But let's do up to number 4. Up to number 4. Here I'm trying to write these structures so that when we start discussing, we don't have much time to waste. Good. That one I'm done. Maybe for this one is very clear. This one is very clear. We can do it very fast. Now, number 5 is yours to try out. Number 5 is yours. Then I have still 2 numbers down, but you'll get them. You'll get them in your free time. You try them out. We still have 5 minutes, so let's utilize. Let's utilize our time very well. Someone is saying that, teacher, I'm not understanding. From where? Please don't forget to utilize the rules. The rules are also up here. The rules are here. The nomenclature rules for alkenes are the ones we are supposed to follow. The reason why, teacher, the number of bonds have exceeded. Let me see. On which one? 1, 2. Oh, yes. Thank you. Thank you. Thank you. That is good observation here. the number of bonds exceeded. So let me rub it off. I think now it is clear. Now it is clear. There it becomes more clear. Okay. 4, 3, 4, 2, 3, 4, 1, 2, 3, 4, 2, 3, 4. Okay. So in the remaining minutes, can't see number 6. Zion, don't worry. You finish up to number 5. Number 6, you'll try it out later because you have number 6 and number 7. You'll be trying out those ones first. Number 6 and number 7 will be for next. That is good. I'm seeing very good answers there, and which are very correct. That is good. We have 1 minute to go. Master number 5 isn't being seen very well. Scroll down. Okay. So can you see it, Herbert? Herbert, let me hope you have seen it very well. Okay, it is time. Can I have someone raising up the hand? Anyone ready to share with us? Anyone? Hey. Okay, Asimwe. Let me start with Asimwe. I go to Imlan, Gilbert, Ken. Asimwe, let's be faster. Asimwe. Jonathan. Jonathan. Jonathan, we are going to leave you. Imlan Khan. Imlan. Imlan. Good.
Yes, sir.
Okay, tell us.
Number 1 is propene.
You're going to give us 2. Number 1 is?
Propene.
Propene. Let me write it there very fast.
Because there are 3 carbon atoms.
Then here?
Then number 2 is pent-2-ene.
Pent-2-ene. This is good. Thank you. Can we clap hands for him? Thank you very much. That's good, Imran. Let's go to another person. Bracing. Yes, bracing. Blessing. Naum. Okay, bracing is ready. Bracing, you speak.
Could I start from number one?
No, number
Or
one,
I continue from where he reached.
But do you have a different answer for number 1 and 2?
They are the same.
Okay, that is okay. Now you tick those ones. Now give me number 3.
My number 3 is hex 1 in.
Hex 1 in. Good, very good. That is good. Let me allow another person so that we have many people who have participated. Thank you, Blessing. Naomi, you're ready now. Yes, Naomi.
Yeah. Yes, for number 4, I got 2,3 methyl hex 2 in.
Oh, first wait, I write. 2, 3,
2,3 methyl hex 2 in.
Methyl hex 2 in, like that.
Sorry, dimethyl hex 2 in.
Very good. I thought you were missing out the di. Dimethyl pen 2 in. Very good. Can we give her a hand clap? Thank you. Now, thank you. That was good. I think we are doing well. Then we have Gilbert. Gilbert. Gilbert is ready. Yes, Gilbert.
My number 5.
Number 5.
Number 5, I got 4 ethyl.
4 ethyl.
Sorry, master. It is 3, 4 diethyl.
Diethyl.
Then 3, 4 dimethyl.
Dimethyl.
Yes.
Oct
2 in.
Oct 2 in. Let me first check whether we are together. Let me see. You have on methyl, you have on methyl, you have 3, 4.
Yes.
And also on ethyl, you have 3, 4.
Yes.
Is it possible? Okay. But you have done a great job. Let me first. Okay. You first mute and we see someone else. We see whether we have someone else with a different answer. Let me have a girl here. Babi. Babi, are you there? If you're not there, let's have Charlie Sima. Charlie Sima Juliet. Charlie Sima. Okay. Priscilla. But now we put down the hands if we. Priscilla, okay. Priscilla is ready.
Teacher, me, I have for number 5.
I'm going to write your answer.
I have 3,
3. Sorry. 3, 4. Okay.
Diethyl.
Then
5, 6.
5, 6.
Dimethyl.
Oct
2 in.
Oct 2 in. Can we first clap hands for? Is that Priscilla?
Yes.
Let's clap hands for Priscilla. That is very true. Thank you. Thank you. That is good. Yeah, I can see people. I believe the other gentleman has known where we got an error here. Because I believe when we are counting, we counted from here 1, 2, 3, 4, 5, 6, 7, 8. So we can see the methyl groups are here. The first one is on 5, another one is on carbon 6. Then ethyl groups are here on carbon 3 and then on carbon 4. I think that one is clear. Someone is saying number 4. Number 4 has a problem? Who is that one saying number 4? Please, now, can I have people put down the hands? If you have a question, you leave your hand up. But if you don't have, let's put down hands. Kindly let me see hands down. Good. Let me see hands down. Dorcas, you have just raised. Dorcas, unmute and tell me. Dorcas? Dorcas?
Teacher. Yes, teacher.
You have a question?
Yes, teacher.
Where?
On number 4. On number 4.
Tell
number
me.
4. Teacher, for me, my longest chain has only 5 carbon atoms. So I have 2, 3 dimethyl.
First wait, Dorcas. Your longest chain has only 5.
Yes, teacher.
Hey, oh. Hello. Okay.
Yeah.
Okay, that is good, Dorcas. Dorcas, that is very good. It seems it is very true. Let us see. Let's count together, remain on call. Now, let's see.
Yes.
We have 1, 2, 3, 4, 5.
Yeah.
Where did this person get 6?
I don't know.
Oh, this is wrong. Are you saying that? Yeah, that is good. That's good observation. So, which means it is our branches are on carbon 2 and on carbon 3, which will be 2, 3 dimethyl pent. Yeah.
Pent in.
Pent 2 in. Good.
Yes,
so
teacher.
this one we cancel it and tick this. Can we clap hands for this lady? Let's have hands for Dorcas. Good.
Clapping for me.
Okay, now for the remaining numbers will be yours to try out. That is the number 6, number 7, number 8. Let's try them out. I want us to look at just a hint on isomerism, just a reminder. I believe we already know isomerism, but I just want to look at a reminder. Anyone who can read for us what isomerism is? Awoli, where are you? Let's put down hands so that we put up when we have. Awoli, you can speak.
Teacher?
Yes.
Teacher, first of all, I want to know how do we, for the previous numbers, how are we able to get the formula from those lines?
Oh, how are we able to get the formulas from these lines? Very good question. Now let's keep there and we move together on this. Yeah?
Okay, teacher.
So on this one, where we see at the end here. Now let's see. Here at the end, it means there is a carbon atom here. On the corner, any corner you see, there is a carbon atom. Even here there is a carbon atom. Even here there is a carbon atom. Even here there is a carbon atom. And even here there is a carbon atom. Are we there?
Yes.
Now, this carbon atom and this carbon atom 1 and carbon atom 2, they have a single bond in between them. So because they have a single bond, and we know that carbon can have a maximum of 4 bonds attached to it. So if they have a single bond, meaning that this will be CH3, and single bond which is joining to this carbon. Are you seeing that? Then we have also
Yes, teacher.
CH2. Then we go to this carbon atom in the middle, this one. But now this carbon atom here in the middle, it has a double bond. There's a double bond, and at the end, there is also another carbon atom. So because it has two bonds, which means this one has only 2 hydrogen atoms to make them 4. But don't forget that this carbon atom still has another branch here. There is a branch, and this branch has a carbon atom which attached to another one, which is at the end, CH3. I think that we have come to the end of our chain.
Yes, teacher.
Which name can we give? You tell me the name for this. Tell me what's the name. Even other people can try. Number 7. You can put your answer as a word is telling us.
So, teacher, according to what I'm seeing, I think it is 2-ethyl.
2-ethyl.
2-ethyl butene.
Butene, like that?
Yes, teacher.
Let us see the longest chain. So your longest chain, you have made it this. Yeah?
Yes.
Why not this one? Yes?
Yeah, that's what I thought.
Yeah, but it's true because this one, when you move like this one I'm showing, this one, it has no double bond. Yet our longest chain should be the one which is having the double bond. So which means our longest chain will be this one, and then the other one will be the branch. So you're very right.
Yes.
This one becomes correct. Though it is also okay for us to put the position of the double bond. It is built 1 in.
It's 1 in.
Yeah. I believe now you can go and practice for number 8 and also practice for number 6 and generating those structures. Yeah.
Yes, teacher.
Kale.
Thank you, teacher.
Welcome. Isomerism. When you talk about isomerism, we are just looking at the existence of substances in different ways, but they are having the same molecular formula, but they can be arranged in different styles. So that is isomerism. And here we just say that the compounds with the same molecular formula, but different arrangement of atoms. So those compounds are the ones we call the isomers. And they undergo the process, that process is the one we call that existence is the one we call the isomerism. Existence of compounds with the same molecular formula, but different arrangement of atoms. That is what we call isomerism. And alkenes have 2 major types of isomerism. Number 1, we are saying we have the structure isomerism, and number 2, we have what we are calling the geometric isomerism. The structure and geometric isomerism. By show of hands, who can tell us what structure isomerism is and what geometric isomerism is? By show of hands. Let me see. Let me see hands up. Mose, where are you? Yes. Hey, Mose, you unmute. Mose? Okay, good.
Good afternoon, sir.
Good afternoon.
I'm going to define geometrical.
Geometrical, okay.
So geometrical isomerism,
Mm.
this is just the existence of a compound
Mm.
with the same molecular formula and structural formula, but differ by prevention of free rotation around at least one double bond.
Differ
by prevention of free rotation.
So you're saying that they have the same molecular formula and even the
structural formula.
Structural formula, but the difference is
But they differ by prevention of a free rotation around at least one double bond.
Oh, rotation around the double bond. Good. That is good. Thank you very much. That was Modest. Can I have another person tell us structure, isomerism? A girl now. A girl. There's this girl called Maga. Maga, yes. Yes, it's ready. Yes, Maga.
Yes, teacher, good afternoon.
Good afternoon.
So, teacher, I'm defining structural isomerism, sorry.
Good.
So, structural isomerism is the existence of compounds that have the same molecular formula but different structural formulae.
The same molecular
formula but different structural formulae.
But the structural formula is different.
Yes.
What are the types of structural isomerism that you know? How many are they?
I remember one.
Like which one?
The chain isomerism.
Okay, chain isomerism. Are you seeing here? Chain isomerism. Are you seeing it here on the screen?
Yes, so, I'm seeing.
In chain isomerism, they have different carbon skeletons. So they have the same molecular formula, but the skeleton of the carbon atoms is different. And I want you to give me those isomers which have this molecular formula. Please, even other members, I want us to get examples of isomers, the chain isomers for this. Let's put them in our chat. And also the one who is on call now, you can tell me if you're ready.
A minute.
Okay, a minute is given to you. By 41 minutes, I'll be asking you to tell us. Even other members, you'd be trying so that you are able to score yourself and see whether you're right or not.
This is bit 1M. We have CH3, CH3,
It's already 41 minutes. As you can remain on the call, you will tell us, but I may have also another person who seems to be ready. Who is this person? There is this one who has PIQX. PIQX. Yes, PIQX. Okay. PIQX. What about Dr. Rich? Dr. Rich. Dr. Rich, are you ready? Okay. Okay, Imlan.
Like the structure formula, right?
First tell me the name.
The name is not pentane. It's butane.
It is it?
It's butene. Sorry.
Okay, butene. Then the other one is what?
Which one?
The
we were supposed to make two of them.
Yeah, so I want the second one.
Oh, I had not finished with the other one.
So which formula? So I just write the formula for butene. Okay, it's okay. I also know this one. 1, 2, 3.
CH2s.
Like that?
Yes.
Okay, now I need the second one.
Okay.
Is it?
I think I've tried out one.
Is it the same as the one they have given us?
Yes, teacher, but I had written but one in. I don't know if it's the same with butene.
Yeah, it's but one in. Yes, yours is much better, I think, because it has the position of that. Then.
Okay, then the second one, I've done 2-methyl but one in.
2-methyl
but one in.
Beauty.
No,
Check very well.
Prop
Yes?
one in. Prop one in.
Prop one in. Okay, yes. I know also how to write that since they are 3, which means there is like 2-methyl. On the second carbon atom, we have a methyl group. So you have a methyl group here. And then we also have a double bond, 1, 2. And then we have CH2. Is it what you have?
Yes, teacher, that's what I have.
Okay. Any other person having a different response? Because I see these ones are having 1, 2, 3, 4 carbon atoms, 3, 4, 5, 6, 7, 8 hydrogen atoms. I think that is very okay. Someone is saying cyclobutane. Now, when you talk about cyclobutane, it is like this. But cyclobutane, but is it, this will be C. Hello, is cyclobutane under chain isomerism of alkenes? No. That is an alkane. Here we are looking specifically at alkenes. That one could be correct if it was a question which is general, and they're asking us to just give isomers which are present in that. So that one cannot work for us. We have 15 minutes and we still have a lot to discuss. So position isomerism. So this is where we're saying that they have the same molecular formula, but differ in the position of carbon-to-carbon double bond. So the position of carbon-to-carbon double bond is the one which is different for these ones. And we have already given you an example of butene, where one is having the position at carbon 1 and the other is having the position at carbon 2. So this one, if I had to draw it, it will be CH3, CH2, CH, double bond, CH2. Then this one, the double bond is now on carbon 2. On carbon 2. And that is... So I believe you see the difference is the position of the function of this functional group, the double bond. Any question? I want us to look at also geometric isomerism that we end with geometrical isomerism. Someone is having the hand up. Let me first see what's the problem. Audrey?
Yes, teacher, I have a question. It's on chain.
On chain, yes.
When we are given, let's say the butane, that's C4H8, that's butane. You first draw its structure, then you condense it. So then you had that first example. That will be like, oh, I'll still keep it under butane. So I don't know if it's a weird question, but why isn't it that the isomers have the same names since they are got from the same compound?
No.
Why don't they?
Oh, okay. There's someone who wants to answer. You remain on the call so that this person can give us the answer. Who is this? Samuel? Samuel? Do you have the answer for her? Samuel? Samuel, do you have the answer? Okay, Ruth Namakula.
Yeah.
Hey, yes, Samuel.
Yes, I had.
You have the answer for Audrey?
Yes, I had her answer.
Okay, yes, please.
Yeah. So I was trying to inform her that when we are dealing with the isomerism, like maybe if it is chain isomerism, it is not necessary that the isomers must have the name of the given kind of hydrocarbon we are considering. They might change.
Actually, we are calling them
so the
isomers.
Of the isomer.
What is the definition of the word isomers? What are
Yes,
isomers?
so that is what I was going to explain.
You know the definition, Audrey?
No, that is what I'm going to tell Audrey, that the definition itself is what explains why they are not the same. They are just not the same because they have different structure formula. So since they define structure formula, I cannot have butane remain butane when I displace as a methyl group in this particular carbon skeleton, for example. So it cannot remain the same compound or with the same shape. So it has to like get another name. Yeah, that is what I had to explain.
Okay, could you tell us what isomers are by definition?
They are compounds which have the same molecular formula but have different structure formula.
They have similar molecular formula, but they have
differ in structure.
But they differ in structure formula. Okay. So isomers, different compounds that have the same molecular formula but different. So when you use structure, you're coming direct to structure isomerism. Yet we have also geometrical. So instead we can use but different arrangement of atoms leading to different structures. Are you seeing that? I think that one can be more clear, so that we are not specifically diving on the
Talking
side
about
of structure. Yeah.
Okay. Thank you, teacher.
Okay. So I believe that one is very clear for isomerism. Now we can look at geometrical. Now, for geometrical, we have just tried to summarize that the condition for geometrical isomerism, there must be the presence of double bond. Hey, teacher, no. Dorcas is saying, teacher, no. Dorcas, please, where are you? Unmute.
Excuse me, teacher, I have a problem there up on the nomenclature of chain isomerism. That last isomer we named. I have a question.
Let it come.
Yes.
Let it come here. On the chain. Yes, please.
Yes. So this last isomer for 2-methyl prop 1-ene. Is it necessary to mention the position of the double bond? And yet we all know like it will only be in one place.
Yeah,
you
no.
get?
Yeah.
Is it necessary to mention the position, or I can just say 2-methyl propene?
No, you can you can just mention that one, but also someone who puts that position will not be penalized. Yeah, but even yours will remain the same, because whether you change this double bond to the other side to remain the same. Yeah. Thank you.
Okay,
yes.
Teacher. Thank you, teacher. Thank you, teacher.
Welcome. I still have someone. Ivana. Ivana?
Teacher, thank you. I just had a question. So under structure isomers,
Structure.
yeah, we have three categories: the chain, position, but then we've not spoken about the functional.
The
I was just
functional.
wondering why.
Oh, anyone who can respond, you remain there so that we can have someone. Anyone who can respond to her, she's asking, why is it that we're not having the one for functional group? Someone is okay. I see many hands here. Claire? Claire? Claire, you're not speaking. Okay, can I have Sala, Jovia Sal?
Good afternoon, sir.
Good afternoon.
So for functional isomerism, that's simply compounds with the same molecular formula but different positions of functional groups. Yes.
What is functional isomerism? By definition, they have the same molecular formula but different functional
different functional groups.
So who was let me see the one who was asking. Was it Dorcas who was asking?
No.
There's someone who was asking. It was? Who was that one? Ivana. Ivana, are you the one? Hello? So, if we are to have, let me write it here. If we are to have under structure, the functional isomerism, functional group isomerism, and we are considering C4H8. Now, here we are just looking at the same molecular formula, but different functional group. Are we there? So, which means we can have two. The one they gave us, the one which is cyclo what? Was it cyclobutane? Yes, cyclobutane, and then we have this normal one that we know, the butane. We can have any position. This is but 2 in. This one has a functional group of double bond. This one has a functional group of single bond. So those are two different compounds. They have the same molecular formula, but they have different functional groups. Ivana, are you answered? Ivana, okay, good. Ivana is saying good. Okay. Ruth, you have a question? You people, you have a few minutes and yet, which means we shall start from there in our next lesson. Ruth? Okay.
No, teacher, it's okay.
It's okay. Right. Edith Mbuga? Edith? Okay, allow me to finish geometric isomerism. So we're saying that the condition for geometric isomerism to take place, before I continue, let's make sure that on structure isomerism, we also add number 3, the functional group isomerism. And we even have seen the examples, so that is okay. And when we come for such a discussion, let's always make sure that we bring out all those that at the end of it all, we can make our own notes and we make we expound more on the knowledge that we have and the notes that we have. So we are saying that the condition for this geometric isomerism is a double bond. And we're saying that each carbon bonded to two different groups. Each carbon bonded to two different groups. That's when the geometric isomerism can take place. There must be a double bond, and each carbon atom must be connected or bonded to other two different groups. Someone is saying that you can't see well. In the comment section, let me know whether it's true for everyone. Can I have another person respond in the group and I know whether you're seeing? Otherwise, it's not good to... It's visible. Okay, good. Now that it's visible, the other person is the one to check. Okay, so those are the two conditions. Those are two conditions. And now we have an example. You recall that in geometrical, we have two types. The cis and the what? The trans. Okay, we shall be two examples where we shall be having one which is the cis kind, and then the other one having the trans kind. Now, let me have one person give me the two types of geometrical isomerism that you know. Two types of geometrical isomerism that you know. Or even if there are more, but let me know. Jimmy, you unmute. Jimmy. Yes, Jimmy.
Yes. Good afternoon, everyone.
Good afternoon.
Yeah, now the types of the geometric isomerism. Number one is the cis isomerism.
Cis?
Whereby this is, yeah. Cis, whereby this is where the similar or identical atoms or groups of atoms are in the same plane or side of carbon to carbon double bond. Then the trans isomerism, where similar or identical atoms or groups of atoms are in opposite plane or on the opposite side of carbon to carbon double bond.
Okay, thank you. But when you look at cis, when you look at cis and trans, those are isomers. Cis and trans, those are isomers. Cis isomer is having, even here we're giving you some key points here, that the cis isomer has a higher boiling point and is less stable, while the trans isomer has a lower boiling point and is more stable. So these are isomers. But maybe you remain on the call, and then we see this other person, we see what he's telling us. This person, you remain on the call. Samsung, what do you say? The one with Samsung, I see time is done, but we shall borrow a few minutes, like 5, and then we wind up.
Yes, teacher.
Yes, Samsung.
Good evening, sir.
Good evening.
I think the cis isomers, they have identical or similar atoms on the same side of the multiple bond. Then while trans isomers have them on opposite side. That is what I can say.
Okay, they have on opposite side, while the other side they have on the same side.
Right.
And we can, okay. Jaren Senior. Jaren Senior is giving us some two things. He's telling us stereo and optical. Have you ever heard of these ones?
Yeah.
So you'll find out that there are those ones due to the images, while these ones are due to the cis and trans, just transposing on the same side and transposing on the side different, on the same and then on the opposite side. So those are the two types that we have. And I want you to make the research on these two, the stereo isomerism and optical isomerism, so that next time we're able to move on. But the good thing, we have already given a very good hint that for us to have geometrical isomerism, there must be a double bond. And each carbon should be bonded to two different groups. Unless we have someone who is a burning question, I want to show us our next work that we're going to have. This is our next session that we're going to be having, where we'll be winding up with alkenes. We shall be looking at chemical properties of alkenes, the chemical properties of alkenes. Someone is asking when. The when is on the timetable. When you check on the timetable, the time for chemistry, that's when we shall be having this. But on that day, I believe we shall not have any interruption. We shall be able to utilize the time very well. We finish all this that we are setting up. So our next time, we are looking at chemical properties of alkenes. Please, when I talk about this, the reason why I talk about it is for us to go and make research. And such when we come, we're able to just go through. I already have some notes. These are the notes which I'm going to share with you. So you'll be able to have them. Then, such when we come, we shall be doing the mechanisms and the reactions to those. You can see there is a space. That is space for us to try out, and we do. But I have put for you some few notes which are going to guide us. Those are about chemical properties. So after the chemical properties, we have those ones which we shall continue with still, these ones, in addition to hybridization. Because many learners are talking about hybridization, where we shall be looking at SP and SCP2 plus SCP3. We shall look at this in details. We shall look at this in details. We shall look at the chemical properties. Please, this is for emphasis. Chemical properties of alkenes. Then we shall be able to complete also with this. So after that lesson, the next week, we shall be going to this introduction of alkyl halides, which I believe we shall cover very fast before we go to the next thing. Alkyl halides and aromatic compounds. Anyone with a burning question before we have a closing prayer and we end the lesson? Yes, please.
Teacher.
Yes.
I'm inquiring something.
Yes.
Do we only have studies on Tuesday, or there's also other lessons at second phase?
Oh, other special arrangements we shall be putting in the group. Because you see, we have much work. We may have to create more time so that we have at least 2 days in the week. Starting with next week, we shall see. We shall organize with Mr. Kazva and we see whether we can create more other time. Or we can create our special time, like mathematics, we have early morning. So we can create another time and we utilize maybe in the evening. That will be in our discussion. Yes, in the evening time. But I want to appreciate each and everyone for the participation. It has been a very good session where each one of us has participated. One thing I want to encourage us is to go ahead and do this work which I've given you for research, that next time we are able to go on very fast. Have a blessed time. May God bless you.
Yeah. Thank you.